Hello everyone, now we are going to see about MOS device models. So there are two different types of MOS device models we are having. One is large signal model, other one is small signal model. So first of all we are going to see about what is large signal model. It represents a transistor's full non-linear IV characteristics. So here IV characteristics is non-linear, it's not a linear one. So for large signal model, IV characteristics is non-linear. So using this we can determine different things. One is static bias, that means DC operating point or Q point. Other one we can determine the regions of operation, that is cutoff region, triode or linear region, saturation region. In all these regions how your MOSFET works, that is what we can determine using this large signal model. And also we can find absolute voltage limits. So these are all the different things we can determine using large signal model. So the basic thing we can determine is DC operating point or Q point. What is the drain current equation when your transistor is in linear region? So this is what the equation ID equal. Now we are going to see your transistor working in three different regions and what is the corresponding equation and diagram. So first, this is what the first one, transistor is in linear or triode region. What is your drain current equation? This is what the drain current equation. So ID equal to half mu n Cox W by L into twice of VGS minus VTH into VDS minus VDS square. So ID is nothing but drain current. Mu n means mobility of electron. So here we are considering N MOSFET. We are taking N MOSFET. So mu n represents mobility of electron. Cox means oxide capacitance. W and L, these are all channel width and length. VGS, this is what the gate source voltage, and VTH is nothing but threshold voltage. VDS is nothing but drain source voltage. So this is the equation of drain current when your transistor works in triode or linear region. Next, when your transistor works in saturation region, what is the drain current? So this is the equation ID equal to half mu n Cox W by L into VGS minus VDS the whole square into 1 plus lambda VDS. So this is the equation of drain current when your transistor works in saturation region. And next we are going to see, these are different diagrams. So here this is for MOS models for saturation region. So saturation region, what is the condition for saturation region? So your gate source voltage, that is input voltage, gate source voltage should be greater than threshold voltage. When this condition is true, that is when your gate source voltage is larger than threshold voltage, then only your transistor will be in on state, will be turned on. So and next, for saturation region, one more condition is VDS should be greater than VGS minus VTH. So if these two conditions are these two conditions are met out, the transistor is in saturation region. So here gate is open, source, drain, there are three terminals in your transistor, and here at the drain side we will be having drain current. So ID, what is the ID equation? We already saw this equation. For saturation region, ID equal to half mu n Cox W by L into VGS minus VTH the whole square into 1 plus lambda VDS. So next one is for triode or linear region. So here for linear region, what is the condition is VGS should be greater than VTH threshold voltage, and VDS is smaller than VGS minus VTH. So lesser VDS compared to VGS minus VTH. So when these two conditions are met out, the transistor is in linear or triode region. So here what is the ID current of ID drain current of your transistor when this is in triode region. So half mu n Cox W by L into twice of VGS minus VTH into VDS plus VDS square. And next, VGS is greater than VTH, but VDS is very smaller value. that is very smaller than twice of VGS minus VTH. At this time, the transistor can be viewed as a voltage controlled resistor. So voltage controlled resistor. So what is the resistor here? We are considering that resistor as RON. So what is the equation is RON equal to 1 by mu n Cox W by L into VGS minus VTH. This is what voltage controlled resistor. So in all these three regions, the gate remains an open circuit to represent the zero gate current. This is what about large signal model. So next we are going to see about small signal model. Small signal, the name itself, it represents that we are giving very small signal as the input. So if the bias currents and voltages of a MOSFET are only slightly disturbed by signals, the non-linear large signal models can be reduced to linear small signal representations. So whenever your input bias current and input voltage are very smaller, your non-linear large signal model is converted to linear small signal representations. So and also small signal model is here we are considering for saturation region. So what is the condition for saturation region? VGS is greater than VTH and VDS is greater than VGS minus VTH. So here we are seeing the transistor as a voltage control current source. So how your circuit will be? So this is what your circuit. Here we are neglecting channel length modulation. So there are three terminals, gate, source and drain. This is what about your MOSFET. So your input voltage here is VGS and your drain current is equal to GM VGS. This is what the diagram. Here we are neglecting channel length modulation. When you are considering channel length modulation, in practically we cannot neglect channel length modulation. So when you are including that, your circuit will be like this. So here this is what gate. So gate, drain, source, input voltage is VGS and this is what your drain current GM VGS and this is what your output resistance when you are considering channel length modulation. So now we are going to find what is this RO equation. So R equal to generally V equal to IR, so R equal to V by I. So R naught equal to VDS divided by ID. Now we are inversing that, so we will get dou ID by dou VDS inverse. So we are inversing that equation. That means change in drain current with respect to change in drain source voltage. So we already know for here we are considering small signal model is for saturation region. So what is the saturation region equation is ID equal to half mu n Cox W by L VGS minus VDC the whole square into 1 plus lambda VDS. So now we are going to find what is our R naught. To get R naught, we just consider dou ID by dou I. So dou VDS by dou ID. We are having ID. ID, when you are differentiating this ID with respect to VDS, we will get this value. So that's why we have inverse this equation here. So ID we are having. Now I am going to differentiate this ID with respect to VDS. So what we are going to get is this. First I am going to expand this one. So 1 plus 1 into this value plus lambda VDS into this value. So 1 into this one the constant only. Here there is no VDS, so this will be considered as constant. So when you are differentiating constant with respect to some value, that value will become 0. So dou ID by dou VDS equal to this value will become 0. Next we are having lambda VDS into this value. So when you are differentiating this with respect to VDS, what will happen? This value will become 1, so lambda into this one. So lambda into half mu n Cox W by L into VGS minus VTH the whole square. This is what we are going to get when you are differentiating this equation with respect to VDS. So that is dou ID by dou VDS. This is nothing but RO. So RO equal to dou ID by dou VDS. We have to inverse this value. So 1 by this one. This is what actual R0, 1 by this value. So this is approximately equal to 1 divided by lambda into ID. We are considering this as ID. So approximately equal to 1 by lambda into ID. What? R0. That is output resistance when you are considering channel length modulation. This is what about small signal model equation. Thank you for watching.